This is the last problem which we've solved in the class, so I'm going to give you some comments to this problem in addition to the slides in the notes. So of course, first we gotta start from drawing a picture. A good picture is a large picture, a big picture. So first, a prism. (35° angles here, and the glass has a coefficient of refraction. Standard number is 1.5, and a round has a coefficient which is equal to 1. So now we've got a horizontal beam approaching toward the prism. Here the refraction is happening. So first, we cannot do anything else. We cannot write the law because we don't see the angles, and we don't see the angles because we don't see a very important element which we call the normal. And we call it the normal because in physics this word means perpendicular. So first we have to draw a straight line which is perpendicular to the boundary between air and glass. So this is the normal. Now, without this prism, light would have been traveling straight ahead like this. This is the direction which we would have absorbed if prism wouldn't deflect the ray. Now, deflection happening due to refraction, and we have to choose between bending away from the normal or bending toward the normal. Well, as we know, when light travels from medium with low index of refraction, n equals 1 here, into the medium with high index of refraction, 1.5, it must bend toward the normal. So the new direction of traveling is like this. Well, now for this point, we can write the Snell's law. Well, the Snell's law connects the angle of incidence and the angle of refraction. Both angles must be measured between the normal and the ray. The normal and the ray. So now we can write the law. N1 times sine of first angle must be equal to N2 times sine of second angle. Well, what is the first medium in this case? That's the air. So for N1 we're writing number 1. Now we have to multiply by the sign of a number. This is the angle we have to use for the angle of the incidence. Do we know it? Well, no. So we must relate it to some other angles we know. For example, we know this angle equals 35 degrees. And in a prism like that, with both sides equal to each other, the bottom angles must be equal to each other. And this angle here is equal to this angle there. And if we would know this angle, to get the theta 1, all we would have to do is just subtract this angle from 90 degrees, because that's what normal tells us. Normal is the line perpendicular to the surface, so 90 minus this gives theta 1. So this angle is equal to that one. This angle, well, let's call it alpha, is the same as this one, and because that's a triangle, the sum of all angles has to be equal to 180. So alpha plus another alpha plus 35 will be equal to 180 degrees. So alpha is 180 minus 35 divided by 2, and 180 minus 35 and divided by 2 gives 72.5 degrees. So this is 72.5, so this is 72.5, so theta 1 will be equal to 90 minus 72.5, which is 17.5. And that has to be equal to, well, the second medium in this situation is glass. And for the glass, n equals 1.5 times this. And what do we write here? Well, that's exactly what we are looking for. That's an unknown, so we just keep a variable. And now we solve it for this variable. So that's going to be equal to sine of 17.5 divided by 1.5 and theta should be equal to the inverse sine of this number. Well, different calculators do it differently. Where is my inverse sine? This is my inverse sine. Oops. $11.5. And since my calculator uses degrees, I don't use radians in any calculation, so that's my angle of refraction for this boundary. Now, when the ray reaches the second boundary, here refraction will be happening again. And well, what do we have to do first? First of all, we have to draw a normal. That's line which is perpendicular to the interface 90 degrees here. Now, without any refraction, the ray would have been traveling like this, but now, because of the refraction, it must bend. How? Toward the normal or away from the normal? Well, because light travels now from medium with high index of refraction into medium with low index of refraction, it has to bend away from the normal. That's the normal. Away means this way. So that's how light will be traveling now. Well, again, we have to write the law. Well, technically that's exactly the same law. N1 times sine of theta 1 equals N2 times sine of theta 2. However, these variables now mean something very different. The first medium now is glass. The second medium now is air. So the best way is just adding some additional symbols so we wouldn't confuse these variables with the old variables. Now for the glass, this number equals 1.5. Now the angle number 1, that's the angle of incidence for this ray. According to a definition, it must be measured from the normal to the ray. This angle is the angle we have to use here. Do we know it? Well, unfortunately, no. So, we need it, but we don't know it. What do we have to do? We have to find it. And in order to find this angle, we have to forget about physics and we have to start doing pure geometry. So it's all about angles. We need to see some geometrical figures like triangles. And if I connect these two normals, I can see that they, together with this line, form a triangle. It's not a right triangle, it's some kind of a triangle, but if I call it, let's say A, well, let's call it B, C, D, A, C, D triangle has three angles. This is 11.5. This is what we need to find. If we knew this angle, we could have gotten this one. So now we have a different problem. We need this angle. We don't know this angle, so we have to find it. This angle, D, let's call it D, is also part of a different figure, A, B, C, D. So that's what I want to redraw, just a little bit bigger. Yeah. A, B, C. Now D somewhere here, and I know this line is perpendicular to this side of the prism, and this line is perpendicular to this side of the prism. That's the first normal. That's the second normal. This angle has to be equal to 35 degrees. So this angle G is a part of this figure which has four vertices, right? And there's a rule which tells us that if we add four angles now, the sum must be equal to 360. So A plus B plus C plus D equals 360, or 90 plus 35 plus 90 plus D equals 360. So D will be equal to 360 minus 1990, 180 minus 35, 180 minus 35. So that's going to be 145 degrees. Yeah. Check. 360 minus 90 minus 90 minus 35. 145. So why did we need it? Because we wanted to use it for calculating this angle. So if we draw a line like this, which represents ray traveling from point A to point C, this angle, theta 2, equals 11.5. And this angle, theta 1 star, is the angle we need to calculate. So 1.5 plus theta 1 star plus 145 equals 180. Theta 1 star is equal to 180 minus 145 minus 11.5. So to save time, 180 minus 145 minus 11.5, 23.5 degrees. 23.5 degrees. 23.5 degrees. And finally, 23.5 degrees. And that has to be equal to, well, for the air, this coefficient is equal to 1 times the new angle of refraction. Well, of course, now we can calculate this angle. First of all, the sine of this angle will be equal to 1.5 times sine of 23.5, 0.598. And now the angle itself will be equal to the inverse sine of 0.598, which is 30, well, let's just round it up, 37 degrees. Whew. So this angle equals 37 degrees. It is the angle of refraction for this boundary. As any angle of refraction, it has to be measured from the normal to the ray, 37 degrees. Are we done? Well, unfortunately, not yet. Because this is not the angle we have to find. We are looking for the deflection angle, or the angle of deflection. This is how it has to be measured. Without the prism or any optical device, this ray would have been traveling horizontally. Because of this optical device, no matter what was happening inside, an actual direction of the ray is different. The ray has been deflected. And this is the angle of deflection between the direction which ray would have been traveling without optical device acting on it and the actual direction. So what do we have to do? Well, it's not about physics anymore. Again, we just used physics twice. First time to write this law, second time to write this law, and it took like 1 minute for each. So the most of this problem is related to pure geometry. We have to look at this picture, but this picture now is not good enough. We know that. A good picture is a big picture. We have to see all these angles very, very clearly. So I want to enlarge this picture to make it bigger. So let's start from a point A again. So we have this side up to the point B. Then, so this normal goes like this, and we have another side which goes like, well, like this. Yeah. So we have this point D, this point C. This again is a normal. Okay. All right. Good enough. Okay. A, B, C, D points are shown clearly. Now what else do we know? This ray travels initially horizontally, and this is how it would have been traveling with no prism acting on it. In reality, it traveled like this from point A to point C, and after that, so that's a normal. This ray has been deflected. That's a continuation of this side. It's been deflected away from the normal, so like this. All right, what angles do we know? Well, all of them. Let's put them. Okay, 145 degrees. Now, this angle here, 11.5 degrees. Now this angle between the ray and normal, 23.5 here, 23.5 degrees. This is 35 degrees. Now, from the normal to the ray, from the normal to the ray, 37 degrees. And the angle we need to calculate is this one, between this direction and this direction. So first we need to extend, well, we can extend it in both directions. So this is direction of the undeflected ray, and this is the actual direction. So this is the angle of deflection. That's what we are finally looking for. Well, if we knew this angle, A, B, C, D, let's call it point E. If we knew this angle, psi would have been equal 180 minus E. So this angle is a part of this triangle, AEC. So maybe we can use this triangle to calculate this angle. Well, let's see what else do we know. The very first angle, theta 1, which has been measured between the incident ray and the normal. That's the normal. This angle is equal to, where was it? 17.5. 17.5. So we have two straight lines crossing each other. These angles must be equal to each other. So this angle, so normal ray, this total angle equals 17.5. So now, finally, this angle will be equal to the difference (17.5) minus smaller angle 11.5, which gives us 6 degrees. 6 degrees. All right. Done with this part. What about this one? That's another one we need. Well. Unfortunately, I didn't have a protractor and I didn't use a ruler to draw this picture as accurate as possible. But again, if we look at this point, we have two lines crossing each other here. This line represents a side of a prism, and this line represents the direction of the ray traveling after the prism, passing the prism. So this angle here, two lines crossing each other, is equal to this angle here. So this small angle will be equal to this angle, and that's supposed to be equal to 90 degrees minus 37. 90, because this line is perpendicular to the surface, minus, and we're subtracting this angle, the angle of refraction. So that's got to be equal to 53 degrees. Of course, in the picture it's much smaller, but who cares at this point? Just keep the track of numbers. So 53 here, 53 here. That's 53. And so from here, I'm gonna use a pencil. From here, from this side of the prism to here, to this normal, this angle equals 90 degrees. So this complete angle equals 90 degrees, but it has three parts, from here to here, from here to here, and then from here to here. So if I add these three angles, I should get 90. So 23.5 plus the angle we need to get plus 53 should be equal to 90. So let's write it down. 23.5 degrees plus a question mark plus 53 degrees equals 90 degrees. So the question mark will be equal to 90 minus 53 minus 23.5. 90 minus 53 minus 23.5, 13.5 degrees. All right? So this angle is equal to 13.5. Well, 13.5 plus 6 plus E should be equal to 180 because of the rule which applied to AEC triangle. And finally, this angle, the angle of deflection, has to be equal to 180 minus 180 minus E, which is 180 minus 180 minus 19.5. 180 minus 180 is 0. They cancel each other. Minus and minus makes it plus. So 19.5 is the angle of deflection. Done. And finally, much faster way for calculating the angle of deflection. If we look at this picture, this triangle is a smaller part of the large triangle. This angle is this angle, which is equal to this angle. This angle is this angle, which is equal to this angle. So these two angles equal 72.5 degrees each. So 72.5 degrees here means this angle here equals 180 minus 72.5, which is 107.5. So if we look at this triangle, 107.5 and the 53 together equals 160.5. So to get this angle, we need to subtract this number from 180, and that gives 19.5. In fact, anybody who likes algebra can prove that the deflection angle will be equal to the difference between the base angle and this angle, which has no name, but equals 53 in our example. 72.5 minus 53, 19.5.